Welcome AP Calc students. In this video I want to talk to you about limits. If you remember from our last video, limits are going to be one of the three big ideas that we talk about a lot this year. And one of the reasons that they are so important is because they are going to build the foundation for us to understand the two problems that we looked at in our first video, the tangent line problem, which focuses on the world of derivatives, and then the area problem, which is the world of the integral. So let's pretend that there are two people having a conversation, sitting across a room from each other, and after a nice conversation, they decide that they want to get up and walk towards each other and kiss. A big old smooch. And they decide that they're going to accomplish this task in a mathematical sort of way. Every second that passes, they're going to take the distance that lies between them and they're going to chop it in half. And so they stand up and they let 1 second pass and they chop the distance between them in half. And there they are. And then another second passes and they chop the distance in half again. And there we go. And then another second passes and they chop the distance in half again. Alright, at this point we're going to zoom in on our two smoochers. Another second passes and they're going to chop the distance in half. Another second passes and they chop the distance in half again. And another second passes and they chop the distance in half again. And again, they're going to chop the distance in half. So you can see where this is going. You probably saw where this was going a few seconds ago. They are never going to be able to kiss, right? That distance is going to get chopped in half and chopped in half and chopped in half and chopped in half and chopped in half, etc. And that distance will never allow them to kiss because there will always be a distance in between their lips. Now, in reality, these people actually would have kissed, right? If they actually decided to take that distance and chop it in half every second, they would have ended up smooching. But what we're talking about when we talk about a limit is what's happening not necessarily at a point, but as we get infinitely close to a point. So the answer to this question, what is the limit of the function, or in other words, the distance between the kissers as they approach each other, what's happening is that they're kissing, right? They are going to kiss each other. By looking at what's happening before the event of our kissers kissing, by looking at the fact that their lips are getting close to each other, and in fact they're getting infinitely close to each other, so that the distance between those people's kissers is infinitely small, by looking at that pattern, I can use that pattern to predict. It allows me to have the power of prediction and say, I'm going to predict that even though I can't see them kissing at a certain moment, I'm going to predict that eventually they will, in fact, kiss each other, even though mathematically our example would not have been possible, right? So let's think of it this way. And this idea is not my own. I should make a disclaimer. But I think it's helpful in understanding what's going on with the limit. If you're looking out your kitchen window and you see a function that looks like this, with an x-axis and a y-axis, and you notice along your x-axis that you can see 1, and I ask you, what do you think is happening when the x value is 2? You'll notice that the 2 value is behind this part of my window, right? I can't see what's going on at the 2 value, but I can use reasoning to assume that it's going to be that point right behind my window, right? So whatever this y value is going to be, maybe that would be, what, 1/2 or a little bit more than a half, I could make the assumption that that what's going on at x equals 2 is that my output value is 1/2. But the reality is that any number of other scenarios could be happening. We do not know what's going on behind this window stick. What would you call that? A window stick. Right, so if you look at this example, if I were to ask you to identify f of 2, my output value, and when my input value is 2, is going to be, let's see, whatever that value is, which we had just said in the window picture that was maybe, I don't know, let's just call it 2/3. Doesn't really matter. Or it could be that our scenario is one that looks like this, where if I asked you to identify what's going on at the point x equals 2, you would say that f of 2 is actually not 1/2, right? It's not defined at that point, it's defined at this point. This graph, this function, has a removable discontinuity at x equals 2, and it just so happens that the function is defined up here for whatever this y value would be. Let's just call that 3. So in this example, f of 2 is equal to 3. I should just draw my y-axis. Or you could look at this last example and identify the fact that f of 2 is equal to 0 in this case, right? Same scenario, it's a removable discontinuity, but this time it is defined at a y value of 0. So when we talk about a limit, we are not talking about what's happening at a specific point. So to be clear, that is not the conversation. The conversation about limits is a conversation about prediction. It's a conversation about what's happening as you get infinitely close to some point. In our case, 2. So there's some new notation that we want to get familiar with. You're going to see things that look like this a lot in the coming days. And I want to tell you what is going on with this notation. When you see this notation, you need to be in the habit of reading this in the following way. We read this as the limit of the function f of x as x approaches 2. So it speaks of movement here. So what I'm asking when I ask you to find this, if I say evaluate this or find this, what I'm asking you to do is, from a graphical perspective, I'm saying trace your function and ask yourself what's happening as you get infinitely close, or in other words, as I approach 2. And we've already talked about what happens there. It looks like what's happening is that the output value there is somewhere around 2/3. Even though I don't actually know that that's what's happening at that point. I don't care about what's actually happening at that point. I care about what happens as I get infinitely close to a particular value of x. So let's go ahead and look at an example here. I've got a function h of x, some polynomial curve. I have a removable discontinuity right here, and then I've identified another point for us. And I want to look at these two questions, and I want you to, again, practice getting in the habit of reading this and reading this as the limit of h of x as x approaches 2, or in this case, the limit of h of x as x approaches 5. So, letter A, if I ask you to find the limit as h approaches x as x approaches 2, what I'm asking you to do is consider your x value along your x-axis of 2, and ask yourself what's going on as I get infinitely close on my graph to the point where x is equal to 2. Or in other words, as x approaches 2. So I want you to notice something here. What I'm going to do is trace my eyes along my graph as I get really close to this point. These are like our kissers getting really close. And notice that I'm going to come from both directions. And this is going to matter a lot starting, I think, in the next video. I'll talk about one-sided limits. But I'm approaching from both sides. And what I'm asking myself is, where does it look like my graph is going as I get infinitely close to the point at which x is 2? And what you should notice is that it looks like I'm going to get infinitely close to a y value of 1. So the answer to letter A is, in fact, 1. And if you're scratching your head, you're probably thinking, yeah, but what the heck? I know that h, that's an h, I know that, heck. You're probably thinking that h of 2 isn't 1. H of 2 is 3. And this is true. You're correct. That is a true statement. My point is defined here at a height of 3. But again, with the conversation around limits, we do not care about what's going on at the point. We care about, where am I approaching? What am I getting infinitely close to from either direction as x approaches 2? So again, we do not care about this. Let's look at letter B. What I'm asking is for you to find the limit of the function h of x as x approaches 5. So let's go ahead and find 5 on our x-axis, which is here. And what I want to do is ask myself, not the question of what is this point, but I want to ask myself, as my eyes move along my function, as my x values approach 5 from both directions, that's important, where do I get infinitely close to? What am I approaching? And hopefully you can see that when we're over at 5, we're getting really, really infinitely close to the point, or a height of 4. So it is true that the answer to this is 4. And this one's different than letter A, because what you should notice here is that h of 5, which is 4, is the same as the limit of h of x as x approaches 5. So sometimes it just happens that these two values are the same. And sometimes it happens, as in letter A, that the two values are not the same.